Hello students. So welcome to lecture 5 of the lecture series on filter design. So we have completed 5 parts of the lecture series and we have completed few properties of the FIR filters and we have completely completed the IIR filters and its design also. So in this part we will be looking on the topic that is characteristic of FIR filter with a linear phase. Okay, so what is the importance of linear phase? I think you all know that. So the importance of linear phase is that for system to be, for any system to be distortionless, we need the phase response of the system to be linear phase. Okay, now let us take causal FIR filter. So causal FIR filter means Hn will be 0 for n less than 0 and we are taking Hn is non-zero Hn is non-zero for n equals to 0 to n equal to capital N minus 1 only. Okay, so Hz will be equal to summation n equals to 0 to capital N minus 1 Hn z to power minus n. So h e to power j sigma is equal to summation n equal to 0 to capital N minus 1 Hn e to power minus j sigma n. Okay, now let us say that h e to power j sigma has a magnitude and phase okay, so this is the magnitude and this is the phase. Okay, now as we know that group delay of a system is equal to the phase response minus times the phase response of the system divided by the variable that is a discrete frequency, and the phase delay is equal to differentiation of the phase response of the system with respect to the discrete frequency. So these are the two very important formulas. Equation number 1, this is equation number 2. Now let us take the condition of linear phase, that is, let the system has linear phase with the phase response equal to minus times of alpha into the discrete frequency, that is sigma. So we can say that in this case the group delay will be equal to phase delay and it will be equal to alpha. Okay, now as we know that h e to power j sigma is equal to summation hn e to power minus j sigma n equal to 0 to capital N minus 1. So writing this as magnitude and keeping the phase as minus alpha into sigma. So e to power minus j alpha sigma. Okay. Now e to power minus j sigma n can be written as in cos and sine. So cos of sigma n minus j sine of sigma n, and writing this e to power minus j alpha sigma into cos and sine. So we'll get cos of alpha sigma minus j sine of alpha sigma. So there's a space constraint here. Okay. So that can be reduced like that. Okay. So I'm writing it in a better format because these PDFs will be given to you as a note. So that's why so cos alpha sigma minus j sine alpha sigma. Okay. Now in the right hand side and left hand side, comparing the real and the imaginary part, we can get that. So we get that n equal to 0 to capital N minus 1 hn cos of sigma n is equal to cos of alpha sigma, and comparing the imaginary part, we get a sine of alpha sigma, right? Now let us just say that this is equation number 3, this is equation number 4. Now taking the ratio of 3 and 4, we get that okay, divided by okay, here we'll get cos of alpha sigma divided by sine of alpha sigma. Now multiplying the equations on right hand side and left hand side, we will get that okay, by cross multiplication of the two terms, we will get okay, by cross multiplying and taking the RHS to LHS, we will get this. Okay, so we have cross multiplied and taking the RHS to LHS, we will get this. Okay, now this will become a sine term okay, so this will become sine of alpha minus n into sigma is equal to 0. Okay, now if I write this equation and expand this equation, then we can see that this equation will be equal to h0 into sine of alpha sigma plus h1 into sine of alpha minus 1 into sigma, and so on, and we will get hn minus 2 sine of alpha minus n minus 2 divide okay, into sigma plus hn minus 1 sine of alpha minus n minus 1 sigma. Okay, so this has to be 0. Now this will be 0 only when only when, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 32 33 34 35 36 37 38 39 40 41 42 43 44 45 46 47 48 49 50 51 52 53 54 55 56 57 58 59 60 61 62 63 64 65 66 67 68 69 70 71 72 73 74 75 76 77 78 79 80 81 82 83 84 85 86 87 88 89 90 91 92 93 94 95 96 97 98 99 100 101 102 103 104 105 106 107 108 109 110 111 112 113 114 115 116 117 118 119 120 121 122 123 124 125 126 127 128 129 130 131 132 133 134 135 136 137 138 139 140 141 142 143 144 145 146 147 148 149 150 151 152 153 154 155 156 157 158 159 1 Hn is equal to h of n minus 1 minus n, and alpha is equal to n minus 1 divided by 2. Okay, so these two should be the conditions for this to happen. Okay, so these two are very important conditions. Okay, now what will happen if these two conditions are satisfied? So if these two conditions are satisfied, then we can say that h0 equals to h of n minus 1, h1 is equals to h of n minus 2, and since alpha is equals to capital N minus 1 divided by 2, so I can say that this is sine of alpha n. So when we put alpha is equals to capital N minus 1 divided by 2 and write the above equation, then we will get the first term is equals to h0 sine of capital N minus 1 divided by 2 into sigma. The second term will be h1 sine of alpha minus 1, so n minus 1 divided by 2 minus 1 sigma, all the terms. The second last term will be h of capital N minus 2, so that is actually equal to h of 1, so the second last term will be h of 1 sine of alpha is capital N minus 2, so the second last term is this. Okay, so capital N minus 1 divided by 2 minus times of n minus 2 sigma. The last term is h of capital N minus 1, that is h0 sine of alpha is n minus 1 divided by 2 minus n minus 1 sigma. So if now again I try to write this equation in the simplified format is equal to 0, so I can see that the first term is sine of n minus 1 divided by 2. So I need to shift this image. Okay, so the second term will be h1 sine of, so this will be n minus 3 divided by 2 sigma. The second last term will be sine of minus n plus 3 divided by 2 sigma, and the last term will be h0 sine of minus n plus 1 divided by 2 sigma. Okay, now I can see that since sine is the odd function, so I can see that this term and this term are opposite to each other. Similarly, this term and this term are opposite to each other. So the first term will this term will cancel this term, and this term will cancel this term. So the third term will cancel the third last term, and so on. And this summation will become 0. That was the requirement. So this is the condition for a linear phase FIR filter. Okay. So what is the condition? That Hn is equal to h of capital N minus 1 minus n. So this is the condition. Now there are two cases. One case n is odd, one case n is even. Okay, so in Hn equals to h capital N minus 1 minus n, so this will be Hn is, so here Hn is symmetric about n is equal to capital N minus 1 divided by 2. So this is a very important conclusion, that for symmetricity, the FIR filter impulse response should be symmetric about capital N minus 1 divided by 2. Okay, so here n is odd, so here n is equal to 9 in this case, so it will be symmetric about 4. Okay, we can see that this is symmetric about 4. Here capital N is equal to 8, that is even. So here it will be symmetric about 3.5. So we can see that. Okay, so this is important condition that you should learn. Okay, now let us take another case. Okay, so in the previous case we have assumed that, okay, so this is 1 and this is 2. So these are the two conditions where the FIR filter can be of linear phase. Okay, now let us take another condition. So we have taken in the previous case that the phase is equal to minus alpha sigma, where group delay and phase delay come out to be same. But if we want a linear phase but where group delay and phase delay are different, then let us take the phase as beta minus alpha sigma. So here the group delay and phase delay will not come out to be same, and applying the same condition that summation n equal to 0 to n minus 1 hn e to power minus j sigma n is equal to mod of the magnitude and the phase, that is beta minus alpha sigma. Okay, now applying the same method that we will be writing these two exponentials in sine and cos, the same method as we have done earlier. Okay, mod of, so I have to shift this, otherwise there will be a space constraint. Okay, so here it will be cos of, so here it will be cos of beta minus alpha sigma plus j sine of beta minus alpha sigma. Okay, so bracket close. Now comparing the real and the imaginary part, we will get n equal to 0 to capital N minus 1 hn cos of sigma n is equal to the magnitude cos of beta minus alpha sigma okay sine of, so there is a minus sign also, okay, sine of beta minus alpha sigma. Now this is equation number 1 and this is equation number 2 for us. Now taking the ratio of these two equations, we will get that the same method as we have done there. Okay, so there's a minus sign also. So there's a minus sign also. Okay, now cross multiplying and taking the RHS to LHS, we will get okay, so there will be plus sign here. So this has to be 0. Now this summation this will come out to be, so let me add a page here. Okay, so this summation will come out to be a sine function n equal to 0 to capital N minus 1 hn sine of beta minus alpha sigma plus sigma n is equal to 0, n equal to 0 to capital N minus 1 hn. So this can be written as beta minus alpha minus n into sigma is equal to 0. Now let us take a condition that beta is equal to pi by 2. So this sine function will convert into a cos function and it will become like this. Is equal to 0. So this summation can be 0 only when, so I am writing the conditions and these conditions are very important, when hn is equal to minus times of h capital N minus 1 minus n and alpha equals to n minus 1 divided by 2. So in the previous part of this lecture we have seen two conditions where hn was symmetric about capital N minus 1 divided by 2. Here hn has to be anti-symmetric about capital N minus 1 divided by 2. So we can prove this also. So for anti-symmetric also there will be two cases, n is odd and n is even. So here n is equal to 9. So hn will be anti-symmetric about 4, that is capital N minus 1 divided by 2, that is 9 minus 1 divided by 2, that is 4, and at 4 the hn has to be 0. So here n is equals to 8, so it will be anti-symmetric about 3.5, that is 8 minus 1 divided by 2, that is 3.5. Okay, so this is the third case and this is the fourth case. So we have seen the four cases of the linear phase FIR filters. The first case was hn is equals to hn minus 1 minus n, that is hn is symmetric and n was odd. Second was hn is equal to hn minus 1 minus n, that is hn is symmetric with n is even. Third case is we have seen here, that is hn is equal to hn minus 1 minus n minus sign, that is hn is anti-symmetric, n is odd, and the fourth case hn is equal to minus h minus, that is hn is anti-symmetric where n is even. Okay, and symmetric and anti-symmetric are about this value of n, that is capital N minus 1 divided by 2. So it is symmetric and anti-symmetric about this value of n. Okay, so these four are the cases. So here we finishes this part. So we'll be continuing in part 7 or the lecture 7 of the lecture series. So thank you guys, keep sharing these lectures and give us the feedback. Thank you.